So value function, approximating the value function, this is the first thing you can do. It's not the only thing we do. We also are able to estimate the policy using a neural network or a function approximator. And then this is, when you just work with the value function, then it's a value network approach, which is the classical one. The most famous one is the deep Q learning. Another case, oh, I think someone wants to come in. The door is locked. If you can't open it, yeah, thanks. No, yeah, that's it. Yeah, oh, okay. So thanks. This is one case. The other case is that you just directly learn the policy. This is approaches based on policy, and that is policy gradient approaches. And then you can mix both of them, because in the policy gradient approach, if you want to still train that policy network, you need to have estimate of the value. And initially, you do it by basic approaches like we did here. But later, people said maybe we can have another value network that estimates the value that we want. So in that case, you are doing what we call it actor-critic, right? So you have a policy network which is acting, and then you have the value network which is giving you a critic or estimate of the values. Now, let's start with a general framework. So let's start with a case that we have one particular policy. So I give you one policy, and I want you to just estimate the value of that policy, right? If you want to go on with tabular reinforcement learning, the thing that you for the state 1 is V1, right? I don't know what that guy is. Value for a state 2 is V, value for a state 3 is V3, and so on. So you have n different values, right? And then you try to estimate it. How you can do it? If you do Monte Carlo, you just go in one state, you sample, right? You sample enough number of times, you go for another state, you sample enough number of times, and then you average them. That is your estimate, right? But we do know this is not possible anymore in practice, right? What you can do instead, you can instead think of a function approximator. Now, what is function approximator? You always think of a neural network, okay? This is what we do at the end of the day. I use the general term function approximator because maybe you want to do something but neural network, but in practice, you know that you don't do anything but neural networks, right? So you always think of a neural network. So what is this guy, this FWNS? This is one function approximator which is approximating this V function, right? Now, what does it do? It has a bunch of weights in it, W, right? These are the weights of the neural network, for instance. The state S goes in. You might ask me, do we really get literally the state S into it? It's a number just, right? We're going to give right representation. We're going to talk about that, no worries. One-hot representation is the easiest one you can do, right? So we're going to do that later on. But you think that right now you're giving just the state into it, right? The state goes in. Then you have a bunch of different weights that you can tune inside this approximator, right? And then something comes out, right? Now, what you hope for is that you can find the right choice of these weights such that this guy is exactly replicating the value function that you are looking for, right? Now, does that wish come true? Right? Yes, because you have a deep neural network, and that is a universal function approximator, right? So it means that if you have a very deep neural network, that is able to show any function, including the value function that you are looking for, right? Now, if you want to learn this choice of W here, you don't really need to know or sample every single possible state anymore, right? You just sample as much as you could. You give them as samples inside your data set, and then you try to train your function approximator based on that data set, right? So that is the big picture here. So this is a function. This is a neural network. It has a bunch of weights, a bunch of learnable parameters. And the only thing that we want to do, we want to just find out the right choice of these weights so that this is going to fit the original value function that we want. So one thing that you might ask me here is that this choice of function, right? This choice of the model that we are doing, neural network, Does it make sense? Well, old days, people had to make a bit sense, right? Look at the problem that they have. Then they would say, okay, this is a continuous state problem. The angle is changing like this. Then the angles close to each other should have roughly close values. So this function should have this property that if I change the state slightly, then the values are also changing slightly, right? So it needs to be a bit continuous. It needs to be differentiable. It needs to blah, 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 things like that, right? Nowadays, we don't need it anymore. Neural network is doing all of it, right? It has all good properties. It does not have bad properties. It's the best guy on the earth. We don't care about it, right? So those things you can find still in the textbooks, but you don't care about that, right? It makes sense. That's it. So now, what you want to do, you want to find this right approximator, right? You basically want to find the right choice of the weights, and those choice of the weights are hopefully giving you the right estimator of your value function for the particular policy, right? Now, would that be better, this estimate that you can get, would that be better than tabular? I guess in terms of complexity, it's quite obvious for you that that is the case, right? Because say, for instance, I want to do the same thing with tabular, right? This means that I could inside the table, few cells, get good estimate for them. Rest of them, I'm going to leave them alone, right? I don't do anything, right? And then they're going to remain 0, right? Whereas, in this case, when I train those weights for those particular states, right? So if I find a good choice of W, which for the state that I can see, it's matching the estimate of the value, right? Then it's going to give me something about the other states as well, right? Something. I don't know if this is the right thing or not, but, well, it's something. It's better than nothing that I had in the tabular case, right? So this is one thing. You actually get something out of it when you train this model, because eventually this fitting of W to the data that you have is not simply giving you the value in the particular state that you have seen. It's also giving you at these states that you have not seen, right? Simply because this functional approach is somehow relating them together, right? So this is one thing. The other thing is that when you update the value of one state, like when we did basic SARSA, right? SARSA algorithm, we had to do this eligibility tracing, right? And the whole idea was that, well, if I get into this state, since I have seen lots of other states, and eventually I have updated the value of those states based on the value of this state, which I am now seeing, maybe I should go back and update them as well, right? So we went over all of this trouble to just come up with the eligibility tracing, whereas you can directly do it here inside the neural network, right? Because once you get a new sample and you update, you're not simply updating the value of that state, right? You're updating eventually the value of everybody. When one weight changes inside neural network, it does not change the value of one particular input, right? Any input going in is going to change, right, at the output. So it's somehow propagating all the impact over these states, which is a good thing again, right? This is what we want, because we do know intuitively that one state value, when the estimate is getting better, that should also make the estimate of the other values better, right? So this is the other thing. And the last thing is that somehow it's going to capture the impact of this state on the value as well, right? So if you train a neural network and you have lots of possible parameters for your state, right? Maybe some of them are useless, right? Maybe some of them are simply redundant parameters. I'm recording them because I don't know whether this is a part of a state or not, right? Maybe some particular angle inside the robot. This is actually totally useless, right? I don't need to know it to evaluate the value, right? But I don't know it in advance, right? If I want to do tabular, then I need to just consider that state as well inside my state space and learn the value for that. Then eventually I see that it is not impacting, right, inside my table. But here you don't really need to do it again, because you do very well know from deep learning that neural networks have this capability to just ignore those parameters which are having no information, right? So it's going to just focus on the features which carry information. And that is a good thing again, right? So this idea in general, I mean, the whole complexity thing aside, from information point of view, it also makes sense, right? Because this kind of approximator is somehow acting as a kind of universal manipulator of all the values, right? Whereas in the tabular case, you just focus on one particular value, you play with that one. And that is not the best idea, right? At least we see it in the environment, right? If one thing happens, if something happens in this particular state of the situation or game, then we can probably have some idea what's going to happen if we just slightly change this state, right? That roughly is the same. So we probably need to go to totally different state, right? So that's the idea. What we can use as the approximator, obviously, we are going to always use deep neural networks. There have been some other ideas like eigentransform, Fourier transform, wavelet transform. People, before deep learning, they used to do that. But nowadays, we don't do them anymore, right? So, sorry. And linear approximator is basically what we did in the tabular case. And I'm going to show that, okay? I'm going to show you that if you just put that function approximator to be a linear function approximator, then you end up with exactly what you did before, right? Okay, now, so yeah, here we are going to focus on these two, linear one, which we just want to get recap what we did before. And I show you that we are not just getting into a new environment. We're basically doing the same thing, knowing a more general case. And then we get into the deep neural networks. One thing is that one of the main reasons that we do it is because of these models being differentiable. So even in old days, people were more happy with linear models as compared to many eigentransforms. And the main reason was that linear models are differentiable. You have weights getting multiplied with things. Whenever you want to take the derivative, you just take the derivative with respect to any weight. That's a very simple thing, right? So they are better, but you're gradually going to see why they are good. Yes? Yeah. No, I mean, the value function is function based on the estimate of Q function you have. You can say what is your optimal policy, right? Do the action. You don't know it. No, you just get the estimates, exactly like what we did. The tablet one, right? If I particular state in action, right? I can sample the environment, right? I just focus on one state in action. I just sample so many times. Then I average them. This is going to give me the estimate of that state, right? Okay, yeah, Monte Carlo or TD. This is why we had it in the other chapter. I do Monte Carlo or TD on one point, one state. I do it in another state, another state, another. It's a few states, right? And then I try to fit my model into the value I estimated at these points. Then I would say if the scene, there is a kind of low-dimensional behavior between all the states, then this model is eventually learning what is the value of the other states, which I do not have time to go over, right? If this is not really the case, well, this is the best I can do, right?
But this is only for one policy. If we change our policy, we have to read.
Yes, but you know that we don't need to really do focus on policy. We can do off policy, right? We can do Q learning. In Q learning, we can sample the optimal policy, right? And then based on that estimate, we can just know what is the optimal Q value in few action state cases, right? And then you try to fit your Q network into those points, and then hopefully this is giving you, again, right estimate for the other state in action, right? That's it. So you really don't need to do GPI. You can do, but you don't really need to do it since you know important sampling as well. Yes. Our estimate. So it's a kind of noisy one, right? And it can hugely overfit, right? So all of those troubles are there here as well, right? And we can do nothing about that. Questions? So the idea is clear, right? Okay, great. So if you got that one clear, so I have just a few slides. Last time I did it more, and then people told me you can trust us. We do remember deep learning. So I'm going to do it just a few slides to recap and also give you the notation. As I said, I believe that most of you had some contact with deep learning. It's good to recap. One thing that I should mention here is that I am not going into things like backpropagation. These stuff are not going to be a part of the course. But if you want to implement anything, you need to be able to implement a neural network. And whatever I say here, like inference, I don't know, model update, things like this, should make sense to you, right? So you don't really need to know what is CNN to follow the course. But at the end of the day, if you want to implement anything that I told you here, you need to really use a CNN, right? And my personal experience is that as long as if you don't know really what is CNN, then it's going to be a bit hard to understand why this is going to work, right? But as I said, I'm not going to specify the model or anything in this course. So if you had it a long time ago and you want to recap, that's totally fine, right? As long as you're fine with these notions here. Now, how we do function approximation? Well, typically we get a bunch of samples here, right? These samples are the input to the function. X is the input going into the function. Y is the output coming out of the function. And then you have a few samples of them, right? So in our case, X is something that is representing the state. We're going to call it the feature representation of this state. This is something going inside the neural network. Y is value, right? Action value, something like that, right? Now, I can collect a bunch of them, not too much of them, just a few samples, right? Up to the power complexity that I have, right? And then this totally, again, if I want to collect them, I should do something like Monte Carlo temporal difference, something like that, right? So it means that I start from one state. If you think about the value function estimation, I start from one state, I just sample. Finished. Again, I start the same state, I sample, finish, and I average all of the returns, right? This is the value of this state, right? Okay, so so that guy is more expressive, right? So this is one thing, and now this is the main reason that this works, right? Universal approximation theorem. So probably most of you have seen it, or maybe you have heard of it, at least. And what does it say? It says that if you have one deep neural network, this is pretty much capable of just estimating any function, right? And by any function, it does not mean that it really does it for all the possible functions on the universe, but it can do it pretty much for all of them with a good accuracy. So, sorry guys, so it means that I should spend the rest of my today here. That's bad, but anyways. Okay, so universal approximation theorem, what it says that any function that you have, you just choose it. If you have a deep neural network, then that deep neural network is going to approximate any function that you want with a good accuracy. And if you want to improve the accuracy, what should you do? You just increase the complexity of the model. You increase the number of neurons inside that model, right? And as you go deep, the deeper you make the model is going to be more and more expressive, right? And the expressiveness is going to increase exponentially with the depth, right? So it means that if one model with depth 1 can approximate, 100 functions, then when you make it up depth 2, it's going to be 100 to power 2, right? Depth 3, 100 to power 3, and so on, right? Not exactly the same number to power 3, but like you get the idea, right? The scaling order. And this is why we are happy with deep neural networks. They are perfect in sense of approximation. And this is what we want to do today, right? So, yeah, that is the idea. So maybe I look here. Right? That's better. So now, if you want to just do the training, what you do, basically you just try to make the output of your model at every single data sample that you have matching the estimate that you have, right? And you hope that if you get a new data, you're going to get a good approximation of the true function, which you don't know, right? At the output of your neural network. This second idea is what we call a generalization. So you want this to happen. This is what you hope for, and this is what you do it by training, right? So that is the idea of training. If you want to visualize the model, so this probably is going to help a lot thinking about the function approximator. So what you can say, let's assume that x, the state that you have, is a scalar number, right? And then the output y is, again, for example, value of that state, which is a scalar number. So this is a scalar function, right? And you have a bunch of weights inside that function, which you can change. So if you put some weights, it's going to look like this. If you change the weight, it's going to change. And what you want to do, you want to just find the right choice of weights that is at least passing through every single point that you have inside your data set, right? And hopefully at the other points, like for example, you do know this particular point here, and you try to just tune your weights so that it exactly passes through that point or roughly passes close to that point. And what you hope is that like the original function is smooth enough that when you pass from this point at the surrounding point, it's going to be the same, right? Roughly the same as what your model is giving. Okay, so how do we train a deep neural network or any model? We basically do empirical risk minimization, right? So you have your samples, x go in, y comes out, and then you pass your samples through your neural network. This is what you have as f of x given w, right? So this comes out. This is not necessarily the same thing as you have inside your data set, right? And you're just playing with your w to make it happen, right? And if you want to do that, you compute a sort of loss between these two. Typical loss that we choose here is going to be MSE, right? So whatever the output of my neural network is, minus the estimate of the value I have squared, right? And if you just make that 0, if you minimize that, that is going to at least pass through the same values as you have inside your data set. and then for the other point, it's going to be the same, right? So this is the empirical risk, and then we do the training, right? So everybody knows that, right? There's no question on it, right? No question? Okay, cool. So if you got no question, one thing that I want to recap, gradient descent, right? What is the gradient descent algorithm when you want to minimize this function? What do you need to do? You need to just start from one set of weights. These are the weights inside your neural network. And then you keep on computing the gradient at every single weight, right? And then you just move in the direction of the gradient, right? Everybody's cool, right? And now, if you want to compute the gradient, the basic gradient descent tells you that you need to compute the gradient of the loss function at all the samples that you have inside your data set, right? This is why I wrote it down in this form. In line 4, you're computing it for one sample, so you send one single sample over your network. You compute the gradient. What do you use to compute that gradient? Backpropagation, great. So you remember, backpropagation, you're going to use it to just compute this particular gradient, and then you need to average them, right? So you do all the samples you have, maybe different samples, maybe you have 1,000 samples. Every single of them that you collect, finally you're going to average them, right? Add them all up and divide it by 1,000, right? This is the way that you do. But in practice, what do we use? Do we do this full batch training? No. What do we do? Stochastic gradient descent. We do mini batches, right? So we're going to use mini batches, right? So you're going to just sample one randomly chosen mini batch of data from your data set, and then you try to compute the gradient over that one, and then you average over that one. You hope that this is a good estimator of the regional gradient, and you keep on going, right? That's it. Okay, everybody's cool with deep learning, right? Deep neural network, how to train them. These are things that you know, right? Great. So if you do know that, then that's nothing more that you need to know about deep learning at this point to follow the course. Okay? Questions? No question? Okay. So let me just give you a simple setting where we do this function approximator or reinforcement learning with function approximator. And then we're going to start next Tuesday by doing it completely for the linear models and then gradually extend it to the general case. Okay? So now, when I have this particular value function, so this value function, the estimator, this guy is the value network or the approximator of the value function, right? So this guy that you see here, this guy is the approximator of the value function, right? You have no problem. You feel comfortable that I put that W there, right? Because that W is just representing the weights that I have inside my neural net. Same thing I can do for my action value, right? So I can show it with W. Now the things that I need to do, these are parameterized because I have lots of weights, and the only thing that I need to do is to just find those right weights, right? But how we can use them in practice, so I think I gave you a rough idea how you can do it. You can do it, at least in the prediction, is quite simple, right? You can estimate a few particular sample points, so you just choose few states, you estimate their values, right? And then you use that as a reference, you try to fit your model into those samples, right? And hopefully it's going to work for the others. When it comes to control, it gets a bit more complicated, right? Because the story is different as you're changing your policy, right? As you change your policy, your value is also changing over time, right? And then this means that your value approximator is not simply estimating one fixed function over time, right? This function over time is changing because your policy is changing, right? This is a bit of harder story, and we are going to just get a lot of hard time solving it, right? But that is the key trouble that makes the whole story quite complicated. But let's start with the simple case. This is just a quick recall that the prediction simply means that we have the policy and we want to evaluate it. That is not a big problem because we have a policy. If we have rest of the time you can simply do enough sampling, and by enough sampling, we collect some sample points, then we can learn the value function, right? That is not a big trouble. The main trouble comes when we do control, because we are very limited in estimating the value function, right? In time, because we want to update our policy as well. That is a bit more complicated. Now, let's start with the prediction case. So the prediction should be quite simple for you to follow. The idea in the prediction is that we want to evaluate the policy, and what we can do, we can put one neural network there, right? So this VW is the neural network. That neural network is taking this state as the input, right? And then at the output, it's going to give you the value of this state, right? Everybody's cool, right? Good. So that's it. Now, how we can collect samples? Well, I can start playing with my policy, right? And then I'm going to see a bunch of states. Definitely, I'm not seeing all of them. I see a very tiny subset of them, but that's okay. I just use those samples to estimate the value of those particular states, right? And using those values as estimates, we start to we start to just make our model here to somehow fit this approximation, this estimation of those values, right? Okay, now, first thing, you might tell me, okay, give us one concrete example. This box is nice, blue, very good, but the issue is that we don't see an explicit function approximator here, right? And then let's start with the linear case, the most basic one. What is the linear case? What do you think the linear case would be here? Say your state is one state, which is a scalar number, right? State 1, 2, 3 till state 10, right? How you can do that? What is the linear model? Any idea? Okay, so let's say, yeah, we want to be very naive, right? I give this state, then it gets multiplied with some weight, and then the output is the value, right? It's not going to work, obviously, right? You do know that, right? So this is just a single parameter. I mean, I cannot really make it work, yeah? This is completely obvious for you. And this was not the case that we did when we were doing tabular, right? In the tabular case, when we had n different states, how many parameters did we have? We didn't call them parameters, we just called them empty cells inside the table, right? How many of them did we have? If we have n different possible states, n different possible values, right? Each of them is a parameter. We don't know it, we'll learn it, right? Right? So we had n different parameters, right? We didn't have a single parameter. And then we need to somehow match it, right? So the problem here is that we have not yet defined feature representation of this stage, which we need when we are doing function approximation. So what is the feature representation? So if you have one particular state, then the thing that you want to do is that you want to show it somehow to your neural network, right? And you can just come up with different ideas, right? So in general, what you can say, okay, I have n different possible states, right? For every single state, I give one representation. And obviously, you want this representation to be as large as possible, because the larger it would be, the more features it's going to carry, right? So the feature representation, it means that you see one of the states that you have, any possible, and then there is one particular transform, which is just transforming that state into another value, right? So if we want to be dummy, we could say like, okay, I have a state 1, 2, 3 till n, then I can show every single state with this index, right? I have a grid world with 16 different cells, right? 16 different states. I would say state 1 is represented by 1, state 2 is represented by 2, something like that, right? I can do that, right? But that is not a very good choice. A better choice is this guy, right? This is actually the one which we have done up to this point, right? What we have done up to this point, we have actually used this one sparse representation or one hot representation. So we say, like, if I am in state 1, then this is represented by one feature vector, which is of size n, right? the value for the first entry is 1, rest of them are 0, right? It's indicating I am in the state 1, right? S1. And then when I am in S2, same vector, everybody is 0, second entry is 1, right? And so on, right? Now, one thing that you see, obviously, if you change this representation of your state, the architecture of your neural network is going to change, right? Because your neural network in the first case is just working with one integer input, right? Whereas in the second case, it's just working with an n-dimensional vector, right? And if you think in terms of a linear model, the first one going to have only one weight, right? The second one going to have n weights, right? And those n weights are eventually those parameters inside the table that you try to estimate when we were doing tabular reinforcement learning, right? So at the end of the day, you're going to have one feature representation. For some simple problems like dummy grid world, it's easy to represent that. As long as you can make sure that you are not missing any information, that's fine. For some more complicated problems, like a super complicated game, computer game, then probably you need to just come up with a good feature representation, right? Maybe the screenshot of the game in a couple of frames is the kind of representative of this stage, right? So you can collect different forms of data for one state, right? And each of them is one representation, right? And which one is the best one? In practice, when you do implementation in some new problem, this is also one of the challenges you need to find out, right? You need to figure out which one is the best one. Now, what we are going to assume from now on is that whatever state I have, so I have one space which is the space of all possible states, right? And this is n different states. In the dummy grid world, it's quite simple. It's like 4, 16, 9 different cases. But in something like chess, this guy has 10 to power 40 different cases, right? And then you need to have a mapping which whenever you are in one particular state, then you have one representation for that, right? If you think in terms of chess, maybe the representation is you go up and take a photo of the board, right? That is one representation, right? This is the state that I am in, right? Okay. Now, when you want to get back to the whole stories that we had before, you should always think in terms of this form. This is what I call it tokenization, not everybody, so please do not use it out of fear because I don't want to be ashamed of myself. Tokenization is something else, but it's pretty much doing the same thing, right? So it's like for every single possible state, you give a token, and then you say that, okay, I have a giant vector, and 1 is representing the state that I am in, right? But obviously, this one is not practical in chess, right? Because that vector should be 10 to power 40 dimensions, right? This is impossible. This is what you're going to do. You're going to find out a better feature representation, okay? So in more advanced problems, as I said, so you need to have a problem-specific feature, and that is sometimes a bit of trouble. But yeah, there are a bunch of examples here. For example, when you're thinking in terms of robot, arm, AI, or any entity which you want to train to just do specific human-like actions, then, well, these things could collect different values for the features of the state. Obviously, one robot here in this room has one state which is proportional to its location, but you can represent it in different forms. How far away is from the walls around it, right? And yeah, things like that, or what is the direction that it's heading to, right? So these are the parameters that are showing the state of that particular robot, right? Or for example, if you're dealing with a computer game, a very typical thing is that you get a couple of frames which are showing that very tiny part of the game being played, right? And that is the state of the game, right? So that is one other representation.